Electric dipole is an arrangement in which there are two charges. So one is a negative charge and the other one is a positive charge, which are fixed in space by a distance, and this distance between these two charges is considered 2a. So from the center of it, both the charges are a distance away. So what are the highlights? That minus q and q are actually equal charges but having opposite signs. One is positively charged, one is negatively charged. Alright, and there is a fixed distance between them, and the charges are quite small compared to the usual charges we talk about. And this whole setup is called an electric dipole. And also we will learn about a quantity called electric dipole moment or dipole moment. Dipole moment is a vector quantity denoted by P, and the value of P is actually 2AQ. When we multiply the charge by 2A, then we get the value, and that value is called dipole moment. But since this is a vector quantity, there is a direction associated with it, and this direction is from negative to positive charge, so towards positive charge. This is the direction of the dipole moment. And why this is important? What is the significance of this quantity or this kind of setup? That is, we will study in physical significance of dipoles. And it is very evident in nature, like the molecules what we see usually behave like dipole. Okay, so molecules like CH4 or CO2, these two molecules behave like dipoles. In normal condition, the dipole moment is zero. It means the distance between these two charges in the molecule, the positive and the negative, are usually together. So there is the 2a part, what we talked about, is usually zero. That's why the whole dipole moment is zero. But they develop a dipole moment when an electric field is applied. So when an electric field is applied, the negative and positive charges are separated by a certain distance, and they develop a quality which is equal to a dipole. But in some molecules, the centers of the negative charge and of positive charges do not coincide. They are always separated by a fixed distance. Therefore, they have a permanent electric dipole moment. Alright, so that we have permanent electric dipoles also. And when we see permanent electric dipoles, we call those molecules polar molecules. Alright, here we talked about poles. So dipole simply means having two poles. Okay, having two poles which is fixed at certain distance apart. That's why di means two, and poles are the two centers. And it is quite important in electrostatics. That's why we have to go through it on a serious note. So when this electric dipole is there, where we call it the two charges minus q and plus q separated by a distance 2a, then the line joining these two charges is called dipole axis. And if these two charges minus q and plus q separated by a distance 2a, at the middle of it we can imagine a plane. Okay, we can imagine a plane at the center of it, and this, if we want to find anything on this plane, the electric field due to these charges, then we are finding the electric field at the equatorial plane. Equatorial plane. Why? Because we actually fixed first the equator. Equator is the center middle part, and we imagine a plane here, and on this plane we can find the electric field. So let us deal with these two possibilities, that we have to find the field of an electric dipole. One, at the point on the electric dipole axis, and on the equatorial plane of the dipole, anywhere in the equatorial plane of the dipole. Okay, one by one we will do it. First, on the axis, on the dipole axis. As you can see in the figure A here, what is happening, that there are two charges, Q and minus Q, separated by a distance 2a. As I've already mentioned, there is something called dipole moment, which is from negative to positive, from negative towards the positive. So this is the direction, what you can see with the arrowhead here for the P. And we have to find electric field at a point P, somewhere on the dipole axis. So electric field due to the positive charge at P is outward. Okay, what you can see here, it is directed outward, okay, away from positive charge. And electric field due to charge minus Q at P is towards the negative charge, that is E minus Q. So let us deal these one by one. So E plus Q, electric field due to the positive charge, is 1 upon 4 pi epsilon naught. Then Q, this Q, divided by R square, the distance from that charge to the point where we want to find the electric field. And this distance is R, this R, minus, because R is the distance from that point where we want to find the electric field to the center of the dipole. Okay, so actually from the charge, positive charge, to that point P, it is R minus A. So this A will be cancelled out. So we will just find out the distance, R minus A, and according to the formula it has to be squared. And in the case of the negative charge, the electric field due to negative charge would be 1 upon 4 pi epsilon naught minus Q, because it is negative charge, and then R plus A, because R is this distance, and then we have to add this extra distance to cover that negative charge. So R plus A square. And as you can see, total electric field is actually adding these two electric fields due to separate charges. And when we add it up, we find that Q upon 4 pi epsilon naught is common, which is taken out. And then inside it is 1 minus R minus A square minus 1 upon R plus A square. And when we do the maths, we find out it is actually equal to Q upon 4 pi epsilon naught multiplied by 4AR divided by R square minus A square and the whole square of these. Now here, since R is way bigger than A, so because electric dipoles are very small in size, and the distance we are covering here is huge, like for example on the screen if you can see, if this is your dipole, then we are finding the electric field somewhere here. So we have to cover this long distance. This is our R. So comparing this big distance R, for that A is way smaller. That's why we will ignore A in the calculation, because the smaller distance, and when it is squared it becomes even smaller. So when we ignore A, then we have to just do the square of R square, which is R to the power 4. So what will happen? It will become Q upon 4 pi epsilon naught 4AR divided by R to the power 4. And since we can cancel this R, and then our new power on R in the denominator will become R to the power 3. That you can see right here. Our electric field is equal to 4AQ and divided by 4 pi epsilon naught RQ and the vector element P. And further you can write it in a more better way. You can write it E is equal to 2 and then 2AQ upon 4 pi epsilon naught R cube. Now this 4AQ is written as 2 into 2AQ, and this 2AQ is nothing but it is P. 2AQ is P, that is the electric dipole moment. So we can write it as P. Alright? Okay. So this is the better way to write the electric field due to a dipole on the dipole axis. Further, we talked about the electric field on the equatorial plane. So as you can see in this figure B, the equatorial plane is a plane which crosses the midpoint of this electric dipole. And in that plane, any point P is chosen. At that point, we have to find the electric field. At this point, due to positive charge, the electric field is radially outward. Let me change the color, radially outward. And electric field due to the negative charge on the point P is radially inward. Alright? And these are the two fields, E for positive charge and E for the negative charge. And then the final electric field is somewhere in between these two vectors. As you know from the vector rule that the resultant vector is always within the range of the shorter angle. Alright? So this is the final vector. Alright? Now, for that, we again have to find the electric field by the individual charges one by one, what you can see in the calculations on the right hand side. So, electric field due to positive charge is Q upon 4 pi epsilon naught 1 upon R square plus A square. Why? Because R is the distance from P to the middle of the dipole. So this distance is R, and we know this distance from the middle of the dipole to the positive charge is A. So if we want to find the distance of the point P from the positive charge, then we have to use the Pythagoras theorem, and the hypotenuse is R square plus A square, what you can see right here. So that's why it is like this. And for the negative charge, again, we have A, we have R here, and negative, the hypotenuse is this. The distance from the point P to the negative charge is again r square plus a square. And as you can see that there is no sign yet, so no negative positive sign, because we are dealing with the magnitudes right now. We will deal with the direction later. So when we include the vectors, the total E is actually minus E plus Q plus E minus Q. I will tell you why it is minus. And then to add these up, we use cos theta. So it is something like electric field due to positive charge when projected on the x-axis. So this will become E plus Q cos theta, and the same, and this is our theta angle, and the same, so this angle theta here is equal to this angle, and the same goes for this. These two angles are equal. So for the same EQ minus, when projected on this resultant direction or the x-axis, it will be E minus Q cos theta. All right, so we have to add these two up, and when we add these two up, what will happen? E cos theta positive Q plus E my negative Q cos theta will be added up, and it will become what you can see here, 2 E cos theta, because the value of minus Q and plus Q in magnitude is the same. So it will become 2E cos theta. All right. So, but still you see the negative direction. Why you see the negative direction? Because we have added one element called P, the dipole moment. And dipole moment is always, let me show you it here, dipole moment is always from negative to positive charge. So the direction of P is towards left and the resultant electric field is towards right. To compensate it, that's why we have put the negative sign here, because we are using P. So though P is the direction of the dipole moment, but the resultant electric field is towards right, that is opposite of the dipole moment, and our total electric field becomes 2AQ divided by 4 pi epsilon naught, and again r square plus a square to the power 3 by 2. And you will sum it up when you find our E plus Q. It is actually 1 upon 4 pi epsilon naught Q upon r square plus a square to the power whole square. And this way, if you do it, you will find that we come up here, and again r is way bigger than a square a. So this distance r is way bigger than the distance a. That's why we will ignore again a here, and we'll focus only on the r, and we get this thing right here. So our E is equal to minus 2AQ upon 4 pi epsilon naught r cube. All right, and 2AQ can again be written as E is equal to P, dipole moment. 2AQ is dipole moment, and if we include this vector part P cap, then we just can write a vector P divided by 4 pi epsilon naught r cube, and this is our resultant electric field due to an electric dipole on the equatorial plane. The last thing to include here is that usually electric field has this element 1 upon r square, but when it comes to dipole, it is always 1 upon r cube. So if we go far from the dipole, the field strength really goes down. It reduces exponentially, that is in the ratio 1 upon r cube, okay, in respect to the electric field due to a single charged body, okay. And when we decrease the size of the dipole, when 2a approaches to 0, when we actually reduce the size of the dipole, when the 2a value approaches to 0, then the dipole can be referred as a point dipole. Alright, so 2aq is called point dipole when 2a approaches to 0, when the size of the dipole is way smaller, like we make it very small. And in this case, we ignore the a element in our calculations and we only focus on the r. And then there are few examples that I urge you to go through it. You try it, okay, try to solve it. There are a couple of, I think, there's only one. So one example is there which needs a big calculation. So you go through it, and we can now focus on the last part of electric dipole, which is dipole in a uniform external field. So let us talk about electric field lines. There are electric field lines, means in the region there is electric field, and somehow we place one dipole here. So one is negative charge, one is positive charge. We have specified the direction of the electric field, that is E, and as you know, E is from positive to negative. So what will happen for this dipole? This is the center of the dipole. Because of the electric field, the positive charge will be pushed in the direction of electric field, and the negative charge will be pulled towards the electric field. And in this way, there will be a force, a torque, a turn force working on this dipole, like this. So a twist will happen, and this twist is called torque, and torque is a vector quantity, okay. We'll talk about it. Let me write it. Torque is equal to P, dipole moment, cross electric field. This is the cross product. So torque is a vector quantity. Now what happens is, actually what we are doing is, the angle between the electric field and the dipole moment is theta. So dipole moment is this direction from negative to positive. So when we talk about tau or the torque, we are doing the cross product, which means we multiply the magnitudes of both these quantity P and E, and then we use sine theta, okay. And again a new vector is formed and we call it this direction, which is not in your syllabus to show this vector because it is a twist and turn force. So we'll only focus on the magnitude of it, and that is PE sine theta, okay. And as you can see in your book, it is written magnitude of the torque is Q into E, that is the force, multiplied by 2A sine theta. Now why Q into E? Why force? Because force will be applied on both the charges, Q also. So this force is towards left side, and this force is minus Q into E. Because F, as you know, F is actually Q into E. Force is actually charge multiplied by electric field is force, or electric field is force upon charge. This we have done before. So from there are two forces working on this electric dipole. One is the force towards the left and the force towards the right on the positive charge. On the positive charge, this force is Q into E. Since the forces are at different points and these two are actually complementing each other, supporting each other, that's why we'll add these forces, and that's why this force is covering two perpendicular distances here and here, okay, and that's why A sine theta is the element included in it. What you can see it here, QE 2A sine theta, 2A because there are two forces, okay, and total torque we are talking about here is 2AQ into E sine theta, and as you know 2AQ is what? P. Okay, dipole moment. So dipole moment multiplied by E and then sine theta. Sorry that I've included vector here. So here we will not use vector even for the P. Even for the P we will not include vector. So this is the magnitude of the torque. Okay, and since torque is again a vector which is not specifically mentioned here, but torque is something like when you screw or when you unscrew from a surface, the screw comes out, so it is towards the outward direction of the screen. That is the direction of the torque. And that is it about dipole in your class for now. And in the next lecture, we will be covering continuous charge distribution in Gauss's law. And I request you to stick with the numericals as much as you can do. You can also check the exercises at the end of your chapter. See you next time.